Welcome to Engineering Thermodynamics Part 2. This first chapter is on what's known as exergy. So let's get started. So learning objectives for the chapter are to examine the performance of engineering devices in light of the second law of thermo, define exergy, which is the maximum useful work that could be obtained from the system at a given state in a specified environment, define the exergy destruction, which is the wasted work potential during a process as a result of irreversibilities, develop the exergy balance equation, to apply exergy balance to closed systems and control volume. The ring assignment is chapter 8 in our textbook. Let's begin our study with defining a couple of terms. First of all, what is exergy? Exergy is defined to be the useful work potential of a given amount of energy at some specified state. It's also known as the availability of the available energy. So we compare systems. We also need to know what's referred to as the dead state. A system is said to be in the dead state when it is in thermodynamic equilibrium with the environment it is in. So in other words, there's no transfer of energy between the two objects. They're in equilibrium. A system delivers the maximum possible work as it undergoes a reversible process from the specified initial state to the state of its environment. That is what's referred to as the dead state. The dead state is the environment. This represents the useful work potential of the system at the specified state and is called exergy. Exergy represents the upper limit on the amount of work a device can deliver without violating any thermodynamic laws. So here you have the example of you have a hot potato at 70 degrees C, and you have the environment at 25 degrees C. So therefore, there's going to be a transfer of energy from the hot potato to the environment. Now, when the hot potato reaches 25 degrees C, well then it'll be in equilibrium. In this case, the dead state is the environment. The atmosphere contains a tremendous amount of energy, but no exergy. That's also important to remember. So let's go over the exergy associated with kinetic and potential energies. These are pretty easy because the exergies of kinetic and potential energies are simply equal to themselves. They're both entirely available for useful work. So here, our book shows the formula for the exergy of potential energy. So this is the potential energy per unit mass, and the exergy of kinetic energy, which is the kinetic energy per unit mass. So remember, like in the case for kinetic energy, it's not 1/2 mv squared, it's 1/2 v squared because this is per kilogram, right? So you have to remember that our book uses those units. Of course, if you know what the mass is, it's easy to get the kinetic or potential energy. You just got to multiply either of these terms by the mass. So here's a very good graph to show you what exergy is. So if you have the total energy available, only part of it is going to be useful. That's unavailable is not related to the exergy. The exergy is only the part that's available for use. The unavailable is the part that cannot be used by even a reversible heat engine. So this is just totally unavailable. So let's take a look at a simple example. Here we have a wind turbine where the wind is blowing at 10 meters per second. The vanes on the wind turbine are 12 meters. And we want to determine the maximum power that can be generated by the wind turbine. So in this case, it's pretty easy because here it's just the kinetic energy. So if you plug in these values, you get 10 meters per second squared divided by 2. Do the conversion to get them in the units of kilojoules per kilogram, 0.05 kilojoules per kilogram. Now, if you want to calculate the power, you're going to have to multiply by the mass flow rate. So here, the mass flow rate is the density times the area times the velocity. So the area, we're going to treat the area here as a circle, so it's pi r squared. It gives us the diameter, so it's we can use the diameter squared if we divide by 4. So this part here is just the area. Here's your density. Here's your velocity. The density he gives us. We can look, I think actually he doesn't give it to us here. We can look this up. This is just for density of air. So we can look this up in the back of the book. But plugging in the values, we get 1,335 kilograms per second is the mass flow rate. And so therefore the power is just the mass flow rate times the kinetic energy. So here you get the kilograms cancel, you get kilojoules per second, which is a kilowatt. So that's the maximum power available to the wind turbine. So we know that all devices aren't 100% efficient. If it's, let's say the conversion is 30%, so therefore 30% of this, which is around 20 kilowatts, can be used to convert to electricity. Let's take a look at another example. This is the Exergy from a furnace. So here, consider a large furnace that can transfer heat at a temperature of 2,000 Rankine at a steady rate of 3,000 BTUs per second. Determine the rate of energy flow associated with this heat transfer, assuming an environmental temperature of 77 degrees Fahrenheit. So in this example, this furnace can be modeled as a simple heat reservoir. And the extra of this heat energy is the useful work potential. In other words, it's the maximum possible amount of heat that can be extracted. So this corresponds to the amount of work that a reversible engine operating between those two temperatures can operate. So we can simply calculate the thermal efficiency of this reversible heat engine. So this is the theoretical maximum, 1 minus T low divided by T hot. These are the temperatures of the two reservoirs. The T hot is the 2,000 Rankine, the furnace value, and T0 is the environment. So maybe you got to convert these to Rankine, Fahrenheit to Rankine, and so you get 73.2%. So this heat engine can convert at best 73.2% of the heat received from this furnace to work. So therefore, the exergy of this furnace is equivalent to the power produced by the reversible heat engine. So here, if you have 3,000 BTUs per second, well, you can multiply by 0.732 and you get 2,196 BTUs per second. That's the maximum amount. So there's obviously some association between reversible work and irreversibility. So here's let's define those terms. So the reversible work, it's abbreviated in our book by W with a little REV, is defined as the maximum amount of useful work that can be produced as the system undergoes a process between some initial state and some final state. This is what's known as the useful work output or input, depending on which way you're going here with the engine. When the process goes changes state between two separate states. So when the final state is the dead state, the reversible work equals the exergy. So here you can calculate simply the difference between the reversible work and the actual useful work. That's what's defined to be the irreversibility. And it really depends on which way you're going here. If you're going from a low state to a high state or high state to low state, depends on which way you want to take this equation. You want to not get a negative sign for I. Basically, that's what you're doing here. They should have defined this as absolute value, but our book doesn't do that. It writes two separate equations. So the irreversibility can be viewed as the wasted work potential or the lost opportunity to do work. It represents the energy that could have been converted to work but was not. That's what irreversibility means. The work done by work-producing devices is not always entirely in a usable form. However, for example, when a gas in a piston cylinder device expands, part of the work done by the gas is used to push the atmospheric air out of the way of the piston. This work, which cannot be recovered and utilized for any other process, is given by the following equation. So this is the work due to the surroundings. It's the pressure times the change in volume. The difference between the actual work and the surrounding work is called the useful work. and it's given by the following formula. WU, W is the useful work, is the work minus the work of the surroundings. So we simply take this equation and substitute it here. So let's calculate this using a simple example. Example 8.3. A heat engine receives heat from a source at 1200 Kelvin. So here's our source, 1200 Kelvin. This is our hot source at a rate of 500 kilograms per second, and rejects the waste heat to a medium at 300 Kelvin. So here's our heat engine. It's taking in 500 kilojoules per second. It's doing work of 180 kilowatts, and it's ejecting the leftover energy heat to a heat sink at 300 Kelvin. So let's calculate the W dot reversible out here in this case. So in this case, we can use the formula we have. The efficiency is given by 1 minus the sink T sink divided by T source, and Qn is given. So here it's 1 minus 300 Kelvin. Remember, that's the sink, divided by 1200 Kelvin. That's the source. Qn is the 500 kilowatts, so that's 375 kilowatts. So 375 kilowatts is the maximum power that can be produced by the heat engine operating between 1200 kelvins and 300 Kelvin, given this rate of energy input. So this would represent the available power if the 300 Kelvin were the lowest temperature available for heat rejection. So let's calculate the irreversibility rate. So this is the difference between the reversible power, which again is the maximum power that could be been produced, and the useful power output. So here we just calculated the W dot rev out, 375, and we're told that the power output of the heat engine is 180 kilowatts. So the irreversibility is 195 kilowatts. So that's what we've lost, right? That's just kind of wasted. So let's talk about a concept known as second law efficiency, and it's abbreviated by the symbol little Greek letter eta times a little couple parallel bars. So here, let's imagine we have two heat engines, engine A and engine B. Engine A has a source of 600 Kelvin and extracts that to a sink at 300 Kelvin. Engine B has a source of 1000 Kelvin and extracts it to the same sink, 300 Kelvin, same sink temperature. Let's say both of them have the same theoretical efficiencies, our thermal efficiencies. Both of them are 30%. So both heat engines reject to a medium at 300 Kelvin. At first, here they take, the heat source is different. One's 600 Kelvin, one's 1000 Kelvin. But at first glance, it looks like that both of these seem to convert work in the same fraction because they're both at 30%. So we might tend to think that they're performing equally well. This one takes in at 600 and ejects it to 300. This one takes in at 1000 and ejects it to 300. The thermal efficiencies are the same. Well, obviously something's different here, right? Because this one's at a lot higher temperature. So that's your first guess that, these heat engines aren't exactly equal. So let's take a look at these engines in light of the second law. And, here I think we see the difference. So if we calculate the reversible, if we treat these as Carnot engines, for example, then we could calculate what the efficiency for the reversible engines would be. That's just 1 minus the T low divided by T high. So in the case of engine A, it's 50%. In the case of engine B, it's 70%. Right? So here, that's where the eta theoretical max comes in. So here, this one, look at it. This one is 30%, but if it was really great, it'd be doing 70%. This one's a lot closer, right, to its theoretical maximum than this one is. So here, the second law efficiency is really a measure of the performance of the device relative to its performance under reversible conditions. So now it appears that engine B has a greater work potential available to it. 70% of the heat is compared to the 50% for engine A, and thus it should do a lot better than engine A, right? That's the problem here. So therefore, we say that engine B is performing poorly relative to engine A, even though both have the same thermal efficiencies. So therefore, we can say that A is a better engine than engine B, even though they have the same thermal efficiency of 30%. So it's obvious from the last example that the first law efficiency alone is not a realistic measure of performance of engineering devices. To overcome this deficiency, we define what's known as the second law efficiency as the ratio of the actual thermal efficiency to the maximum possible reversible thermal efficiency under the same conditions. So this is for heat engines. We define it as eta theoretical over eta theoretical reversible. So in the case of our engine A and engine B, we can calculate this. So for engine A, we end up with 0.3 divided by 0.5 or 0.6. For engine B, we end up with 0.3 divided by 0.7 or 0.43. So here we can see the difference, that engine A is actually the better engine. So engine A, what this means is that engine A is converting 60% of its available work to available potential work to useful work, and for engine B, it's only 43%. So engine A is the better engine again. So the last equation is for heat engines, but there's also other equations for other devices. So for work-producing devices, we have an equation. For work-consuming devices, we have an equation. Though these are kind of reciprocal versions here. And for refrigerators and heat pumps, we're given by the following equation. It's the coefficient of performance divided by the coefficient of performance, assuming it's reversible. So let's take a look at an example on how this works. So here, let's say a dealer selling heaters for a home has just received a shipment of electric resistance heaters that have an efficiency of 100%. So assuming an indoor temperature of 21 degrees C and an outdoor temperature of 10 degrees C, determine the second law efficiency of these heaters. So here we can, the advertised heater has a coefficient of performance of 1. It says it's 100%, so that's a coefficient of performance of 1. So at the specified temperatures of 21 degrees C and 10 degrees C, we can find the coefficient of performance for the reversible heat pump. Again, if you don't remember this, just look back in the previous chapter on second law, and there's a formula in there for this given here. So you can calculate what it is. It's 26.7. So then we can define the second law efficiency. It's 1 divided by that, or 3.7%. So this doesn't look as impressive as the 100, right? So the dealer would not be happy to see this value, considering the high price of electricity. A customer would probably be better off with a less efficient gas heater, right? This is not very good at all. This is why this second law efficiency is useful to calculate for these kinds of things. So you can also determine the second law efficiency directly from equation 811, and so you can plug in that, and again you get 3.7%. So again, this is a good way to do it as well.